Okay, good morning. Um, just a warning, I guess. I don't know what's going on with Henry today. Oh, we're making eye contact. Oh, here she comes. She's been very dramatic. She's not starving to death, okay? I promise you. I am feeding these children probably more than I should. But she has been very dramatic and she spent all morning just walking across my screen. So I'll do my best to control it, but we're gonna get some Henry action today while we talk about the hydrosphere. So in building this module, I decided to split it into two entities. The way that geologists sort of look at the hydrosphere being the water portion of the Earth, and we consider these two entities, we consider the terrestrial hydrosphere and the marine hydrosphere. So we're going to cover these topics today as part of the terrestrial hydrosphere, which I'll explain in more detail here in a second. We're going to look at drainage basins, weathering, groundwater, streams and river systems, and then sediment transport briefly. Here's some new vocabulary for you to look at for terrestrial hydrosphere. Um, so terrestrial hydrosphere, what is that? What am I discussing? When we think about how water is sort of situated on this planet, we look at it in two ways. We look at fresh water and we look at salt water, right? Um, all of the terrestrial hydrosphere is freshwater, and it's situated on the land. Terrestrial just means land. So the water that we are considering for this module, for this particular video, is all of the water that is sort of contained in the land in some capacity. And there's a few different, hi Henry, and there's a few different ways in which it is stored. Most of that water is going to be in springs or in stream systems. So this video is going to focus on the water that's particularly pertains to this green section here. We call it a drainage basin. And we call it a drainage basin because freshwater rain will precipitate down on a mountain. This is called a rain shadow. Basically, the clouds move from the ocean. So we get all this evaporation over the ocean. The water turns into clouds. The clouds move onto land. And when those clouds hit high elevation, they're too dense to move upwards. So they sort of have to release some of that density, and the water condenses and it rains. So this side of the Cascades are very wet and very moist. And they produce a lot of plant life because we get a lot of rain in the P and Dubs. And in fact, the Olympics are the first mountain range that this water vapor is going to hit. And because of that, the Olympic mountains are actually, or parts of the Olympics are actually a rainforest because of how much rain they get. And then Eastern Washington, if you've ever been to Eastern Washington, it's wild. If you drive along I-90 and you go over the Cascades, there is a line of demarcation where it's like it goes from forest to not quite desert, but desert. It's very dry. And that is this effect here. They don't get as much rain on Eastern Washington because these clouds need to release all of that water. And so all of this precipitation occurs on the western flanks of the Cascades. So that's how our drainage basins came to be. Basically, what that means is the western flank of the North Cascades are a drainage basin. They're draining all of that precipitation to the lowest topographic region, which is going to be the ocean. And the ocean is what we're going to talk about in the next video. So the first thing we have to discuss in terms of precipitation and the rainforest effect is weathering. We're going to go back to this concept that we started in the rock cycle, weathering, right? So weathering was the first step of sedimentation in sedimentary rocks. We have mechanical weathering. We talked about this. These are the fragments of pre-existing rock known as detrital sediments, and they can be classified based on sediment size, so clay, silt, sand, and gravel. And it's basically the physical breaking of bedrock into smaller and smaller pieces. And there are different agents of mechanical weathering. So pressure can cause a weathering breakdown, temperature, freezing, thawing, plant or animal activity, salt evaporation. All of these proponents will lead to a breakdown of these rocks. But for the case of the hydrosphere, chemical weathering is by far our most important factor. And you've seen this slide before. So this is dominant weathering process in warm, humid environments. It occurs when water, oxygen, and other reactants chemically degrade, move your tail, the mineral components of bedrock and turn them into water-soluble ions that can be transported by water. Higher temperatures are going to accelerate chemical weathering rates. So this was when I used that analogy of a sugar or a candy mountain. If the mountains are made of sugar and water is constantly raining down on it, that sugar is going to start to dissolve in the water, and the sugar will start to, the candy mountain will start to sort of erode away. But this water that holds these sugar particles are holding these sugar ions and they're transporting them somewhere. Once that water evaporates, that sugar will come back into play. So there are a few weathering methods, chemical weathering methods, that are important for the sake of this class. Oxidization is the reaction of rock minerals with oxygen, particularly iron. So if you've ever seen a nail rust or you've ever seen a fence post rust, that is the chemical reaction with oxygen when iron and oxygen. Here's the chemical symbol for iron. Here's oxygen. When you get iron and oxygen that react and come together, they form iron oxide. And that is this red banding here. We're going to come back and talk about BIFs a little bit later in the term. This is a banded iron formation, a BIF. And basically, this rock is high in iron content. And as it formed, it banded with oxygen in different times of Earth's history and formed this beautiful red rock. This is basalt, a basalt flow that has been oxidized. Basalt has a lot of iron in it, if you remember from the rock talk. This is my favorite chemical equation of all time. In fact, it's my favorite so much that I've got it tattooed on my arm here. This is carbonic acid, the formation of carbonic acid. And this is probably by far the most important, all right, I'm biased, one of the most important chemical reactions in geology. Because when you get water, bear with me here, and water evaporates and starts floating around in the atmosphere as clouds. These clouds of water vapor might bond with carbon dioxide. And maybe you are aware, and maybe you aren't, but we are introducing significantly more carbon dioxide into our atmosphere right now through fuel emissions, through industry. It's one of the biggest greenhouse gases. It's incredibly problematic for a lot of ways, and I'll dive more into that in the climate change module. But when we introduce carbon dioxide and water together, they actually bond and they'll form a compound, H2CO3, called carbonic acid. Basically, our rainwater isn't straight rain, it's carbonic acid. Now, nobody panic. It's not so acidic that it is sloughing off our skin, right? Human skin has a pH of about 5.4. Carbonic acid is actually in the same realm. Any pH, if you're familiar with the pH scale, that is less than 7 is considered acidic. So 5 is acidic, but consider like coffee's pH of 3. And here I am sipping my coffee. Battery acid is 1. You don't want to drink battery acid. Lemon juice is like 2. So just because it's acidic doesn't necessarily make it dangerous. However, it does make it more acidic. And because our carbonic acid, because our rain has a slight acidity to it, it actually dissolves a lot of the rocks on these mountaintops just a little bit faster. You need a little acidity to help dissolve some of those minerals at the top of mountains. Carbonation is sort of the same process. And this is predominant with marble and limestone and calcite, all of which are calcium carbonate. And that particular formula is seashells that have been smooshed into tiny, tiny, tiny little particles. And these shells are very sensitive to any type of acidity. So carbonation is the rock is the reaction of rock minerals with carbonic acid. So this is just a step further from carbonic acid. This is the formation of carbonic acid. Carbonation and so it also mentions dissolution and hydrolysis. Those are further oh my God, Henrietta, stop. I love you so much. Those are further reactions using carbonic acid as the agent of weathering. So water and carbon dioxide are forming in the atmosphere, raining down on us. Carbonation, hydrolysis, and dissolution are sort of the effects of carbonic acid on rocks in particular. It's basically the dissolving of different rocks and the different ways in which it dissolves. I'm not going to dive that hard into it. All you need to know is rainwater is basically dissolving rocks. And as it dissolves rocks, oh, I do dive a little bit into dissolution, but it's literally just another way of saying rainwater is dissolving the rocks um, because it's acidic. Uh, and in the same metaphor as Candy Mountain, if these mountains were made of candy and the sugar were melting off because of this water that was consistently striking it, this water is going to carry these ions down a stream. And eventually, when this water evaporates, it leaves behind that sugar. Um, this is going to go into groundwater. So our next topic is groundwater. Once we get this rain, once we get this precipitation, we're starting at the tops of the mountains, right? Once we get this chemical weathering that has begun to dissolve the rocks at the top of the mountains, this water begins. I feel like I should go back to this image. I think this may help. So we have rain. The rain is striking the tops of the mountain, right? That rain has to go somewhere. Some of it is definitely going to evaporate. There's a whole water cycle that I don't necessarily dive into in depth. Some of that water is going to evaporate, but some of that water is going to trickle down the mountain. The mountain, as you get heavier soils and heavier unconsolidated or not lithified particles, these soils and this sediment basically is going to have what we call pore space. So the sediment has the space between each little particle grain, and water, being water and very small molecules, can make their way through this soil. Um, This is called porosity. So this is normal soil. We see the soil on mountains all the time, in valleys. You might have some compacted soil. This was a slide particularly from my environmental geology class where I talk about the problems associated with compacted soil because we want there to be water infiltration. This is so important. This is actually where we get a lot of our drinking water from. It's from the groundwater. This is why we have wells. If you have a well on your yard, that well is collecting groundwater. Oh, look at me getting ahead of myself. So this groundwater, becomes a part of Earth's system in that it becomes what we call an aquifer. And that aquifer is groundwater, and it changes. It's changing based on precipitation, how much rain we're getting. It's also changing based on how much we're using it. So this is an unconfined aquifer, and we all have this whole area. Skagit has a beautiful aquifer that is just a few feet below Earth's surface. And Skagit River is the base of that aquifer. So Skagit River is technically above that aquifer, in that it's a stream channel, and that the height of Skagit River sort of determines the level of that aquifer and where this groundwater sits under Earth's surface. And we might use it in a well. Some of these aquifers can make their way into confined aquifers. A confining bed would be like sediment, like clay, that is really, really hard for water to permeate through. And we certainly don't want to build a well in clay. That would be awful. Do not recommend. But this area here, we have plenty of unconfined aquifers in Skagit where we get a lot of our groundwater from. Wells are drilled into aquifers in order to extract groundwater. They typically have a limited amount of water and they recharge, or more precipitation comes and refills this aquifer. at a very slow rate compared to the rate of how much we use this groundwater. This is actually incredibly problematic in areas specifically like Arizona. So this is the Columbia Plateau. This is the Colorado River. This is the Grand Canyon, basically. The Colorado River is forming the Grand Canyon through northern Arizona. Uh, and this whole area is incredibly problematic in the sense that it doesn't receive a lot of precipitation, as you can imagine. It doesn't get a lot of rain down here. But humans keep building houses and communities in these areas because they're beautiful, they're fun places to live. Rich people summer homes, or rich people winter homes, I should say. And so water usage is incredibly high down here. Versus the ability for these groundwaters to recharge. Uh, so this groundwater is old and it is being depleted very rapidly. This is called fossil water when the water is so old because it's taken so much time for all this water to build up because there isn't a lot of precipitation in this area. Um, and it's being used at a very rapid pace. There's going to be a water shortage here very shortly, if not already. This was from the Nooksack River floods from 2021. So this is the Nooksack. Here's Bellingham Bay right here, because this is the Lummi Peninsula. And this was from a flood. Basically, when a flood occurs, the groundwater, ooh, let me go back. This will be the groundwater, and the top of the water table extends to the surface of Earth, extends to the ground surface. So that happened because there was so much precipitation at this time, that the groundwater filled to its max capacity, and there was nowhere for this water to go, basically. Like the ground was so oversaturated with water that the water just had to sit higher. And that is the sort of the remnants of how a flood works is the groundwater is so oversaturated. But the other thing to note is how fast this flood receded. In geologic span, anyways. It receded in days. Um, so just because we get heavy recharge doesn't mean that that water is going to stay here. And that's going to lead us to streams and river systems. Henry has some opinions about streams and river systems. It's my favorite topic by far, one of my favorite topics. They're all my favorite topics. So, a stream is defined as a channelized flowing body of water. A complete definition of a stream is as a system in which the biggest part is the drainage basin. It also includes a channel, discharge, and sediment load, which we're going to talk about today. The function of a stream system is to collect surface runoff. So this is just precipitation from mountains, from river systems, and plains next to a stream system. And they transport water and sediments downstream. As these streams flow, they do the work of erosion, transportation, deposition, and these stream systems are shaping geologic landforms like valleys, floodplains, and deltas. So Candy Mountain, we're going to go back to Candy Mountain. As this Candy Mountain is dissolving from acidic rain, that rain is making its way into a stream system eventually and bringing with it this sugar. And a lot of this sugar, I know I keep saying sugar. I'm really just trying to use this metaphor. This sugar that I keep saying are ions from minerals. So it's actually usually silicate or calcite, potassium, nitrate, a bunch of different really important elements are flooding down this stream system. But I think using sugar as a metaphor is just a nice visual. Are flooding down the stream system, and eventually it makes its way into the ocean. That dissolved sugar in the stream system is part of the sediment load that the stream is carrying, and clams and other marine organisms really benefit from these ions. I know, Henry. So there are three main types of channel systems or river systems. We have straight rivers, and these rivers are seen in areas where the landscape is really steep, such as mountains. The stream or river's channel appears mostly straight with a few curves or bends. For example, this is Whatcom Falls. And if you've been to Whatcom Falls in Bellingham before, The stream itself is pretty curvy, but anytime you see a waterfall, the water is moving at such a fast velocity that it's not really moving around. It's not really moving around. It's straight. This water is a straight stream. This is a straight river. Braided rivers, oh, they're so pretty, are seen in a lot of locations in deserts, in plains, glacial outwash, and coastal areas, particularly in this area. The river channel contains these sediment bars. So here's a picture of the channel. This blue is this beautiful braided channel. And within these channels of river, you have these sediment bars. And these sediment bars are really important. And they're made up of silt, sand, gravel, or boulders. Um, the water moves quickly to carry various sizes of rock. So these types of channels might flood, or maybe not flood, but they rise and they fall and they rise and they fall. And as they rise, Henry is being so dramatic. Henry, let me put you on the ground. As they rise, they're able to carry more material with them. So this is an example of a braided river in Alaska. Um, that is relatively low. So this was probably taken in the summertime. Everything's green. I assume it's in the summertime. When the water levels were low, but in the wintertime, this channel might fill with water, move some of this sediment around. But as summer hits and we have less melt, less snow melt, and the river levels fall, we get this beautiful braided depiction. It's really, really beautiful. And finally, a meandering river, and by far the most important type of river type. This is where we see these gentle curves or bends in a river. Basically, a meander is this like S-shaped sinusoidal shape in a river channel. And we see these types of rivers, particularly when topography goes from steep to less steep. So this is going to be in valleys, in plains. The water has the ability to slow down and just sort of like meander and take its sweet little time. This is the Skagit River. And the Skagit River, hopefully you're all familiar with the Skagit River, is technically considered a meandering river. However, I say it's considered a meandering river while also acknowledging the fact that here is a braided section. Here is a braided section. As we move up into the North Cascades, we're going to find the Skagit River has some very straight portions to it. So these rivers can be multiple types of stream systems as a whole system. Once it makes its way down into the valley, it becomes a meandering river based on its speed and the fact that now we're starting to see these S-shaped sinusoidal meanders. And they're incredibly dangerous, incredibly versatile, and incredibly dynamic. And they're really amazing features. But I think that because rivers are so beautiful and so captivating, and there's so many fun things to do with the river, people forget how dangerous and how hazardous a river can be. I say that after dealing with the December 2025 floods. If you were in Skagit at that time, you had a firsthand experience of how dangerous these rivers can be. So, in a meandering river, velocity of water moves generally in the center when it's along a straight portion. So, right here, where my little mouse is, this river, the highest velocity of water is directly in the center of this stream. Okay, that's what these images are depicting. Once these streams start to meander, the velocity of the water actually changes where it's at. And that has to do, okay, the best way I describe this to people who are not physics people is like imagine this water is coming around the bend and it's moving around this meander. The water is going to swoosh to the outside of this meander. If you ever watched like, oh my God, this is so embarrassing. What is the like sled racing in the Olympics? Oh, I should know what this is called. Um, if you've ever seen sled racing in the Olympics, that's what you're gonna get. Basically, if you see a curve on the sled track, they swoosh on the outside of the sled track. It's the same concept with water. Your highest velocity water is going to go to the outside of this curve as it goes around these meanders. Meaning, here's my depiction of a river where we have water moving from right to left. Some anatomical components of this river are the headwaters, where the waters start. 9 times out of 10, it's going to be the ocean. The delta, where the water ends up. Now, it can end up in another river system. It can end up in a lake. 9 times out of 10, it's going to end up in the ocean. This is my meandering channel. I'll move my face again, sorry. Basically, just this shape here is my meandering channel. Now, there are two proponents of this stream system, Henrietta, that we haven't talked about. The cut bank, oopsie, cut bank, which is the outside curve of a meander. This is also going to be a cut bank. This is also going to be a cut bank. Now, remember, when water is coming around a bend and it hits the outside curve of this meander, it's hitting the cut bank. That means it's eroding. This water is moving very quickly. It has the ability to erode this side of the meander. The opposite side of this bank is called the point bar. And because the fastest moving water is on this side of the river channel, this side is actually the slowest moving water, meaning that anything that this river was, Henry's licking my hand right now. She's trying to play coy. Meaning that this stream, whatever it has picked up, sediment, gravel, sand, silt, whatever it has picked up along the stream, has the opportunity to deposit on this side of the river channel. So this side is depositing. This side is eroding. So I want you to think about for a second. You don't have to pause the video, but you can pause the video. If this side is eroding, come back. If this side is eroding constantly, and this side is depositing constantly, what do you think is going to happen with this channel? And now let's imagine, oh, just kidding. I thought this was my other part of the slide. Basically, these channels shift. They move laterally. This channel here is going to move downwards. This channel here is going to move upwards. This channel here is going to move downwards. These channels move and shift, and they move and shift very rapidly. So it will continue to shift and shift because it's continuing to erode this side of the river channel at a regular and constant rate, pardon me. So it's going to continue to erode on this side, making the channel come down here. That would be our new channel. So these meanders change incredibly fast, incredibly quickly. We got our headwaters, we got our delta, we got our meandering, cut bank, point bar. So what happens when we get a flood? Like the December 2025 floods that occurred in Skagit this year. Our flood waters reached 37 point something feet. Normally they're at like 16, 17 feet in Mount Vernon. So they rose almost 20 feet in some places. It was a massive flood. When you get that much water, the velocity of the water is moving significantly faster. It's picking up larger materials and more materials, which means it's going to erode that much faster. Sometimes we get scenarios in which these floods will actually cut off a meander entirely because all of a sudden the floodwaters are like, wait, I can find a faster moving system here. And when you think about it, if we had an old channel that was here, and this channel was moving, 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 and formed a new channel here eventually, we have a little bit of a scar in Earth's topography right here, where the channel used to be. So it's not like, oh, this water is just going to cut through trees and high hills. A lot of times it's cutting through channels that have been there previously, and it will form a new channel, cutting off this meander here. We call this cutoff meander an oxbow lake. This happened in the December 2025 floods. And we're so lucky first of all, we were lucky that nobody was harmed in this because it is a very scary event that happens. It's called a avulsion. It's incredibly scary when it happens, but nobody was harmed when this did happen. This was on the Skycomish River. Yeah, Skycomish River. And this was the channel prior to the December 2025 flood. So this was December 14th, 2025. Let me move my face. The floods started, uh, actually, I think they started on the 10th. Oof, I don't actually remember. They started a little bit before this, but this wasn't when they were at its peak. So the floods were forming this channel. This was the normal channel. But what you'll note is that here's this meander. The cut bank is this side of the river, right? Because the cut bank is always going to be on the outside curve of the river, meaning that this poor road is toast. Same with over here. The cut bank is on this side here. But one thing to note about this as well is look at this. This is where an old meander might have been before the erosion began to really pull this stream channel over in this direction. It is a little creek, or it was a little creek, I should say. So there was still some water sort of trickling through. And then the floods happened. And it changed the channel of this river. So now here's the channel. This was after the floods, obviously. This was the new channel. It basically cut through this creek because the water got so high and was moving so fast. It was like, you know what? I'm not going to go in this direction. I'm going to make the faster route, because water has feelings and emotions and talks like that. So this river system cut through that stream system and it was just like, this is it. This is my new channel. This is my new home, which was good in a lot of ways. So A, nobody was hurt. Yay. B, now this area here has become an oxbow lake. And it is no longer endangering this road. If you look really closely here at this section of the road, you'll note there's a bunch of really big boulders. There's some logs. There's some things. Those were not put there by accident. Those were put there by humans as a mitigation technique to slow the erosion so that it didn't erode this road away. Because that was where this channel was headed eventually. The trajectory of this channel was to continue erode in this direction, eventually erode away the road. Because when they built this road, it was not close to the river system. It wasn't this close to the river system, right? So they put these boulders down. It's called riprap. And they put these along the Skagit River too. So if you ever hike the Skagit River dike in Burlington, you come across these like giant piles of boulder along the riverbank. Humans put that there to help slow the erosion process. But what we've learned, what we know, and we should know, is Mother Nature's going to do what Mother Nature wants to do. So this river system has cut through. We're no longer in danger here, so that's great. And it has evolved. The evulsion process has formed a new oxbow lake, and now this river system runs in this direction. But what people don't understand is that this happens more frequently than I think we think it does. This is the sort of X-ray. I don't know if it's not an X-ray, but I don't know the satellite imagery and time lapse of a river in China. I keep wanting to say it's China, but it's South America. And this is from 1984 to 2012. This is how dynamic these rivers are. This is the change of a river just in, hold on, math, 30 years. That's it. These rivers don't change in a geologic timescale of thousands and thousands of years. They change in terms of decades, which is wild. But it's also what makes them so incredibly dangerous. So imagine Bob builds a house here and he's like, I'm living my best life. He's literally built himself on a cut bank, which is not a way to live. But the problem too is a bunch of rich people are like, I want to live on a river system. What I love about this picture is we can see how Skagit has changed. This loop right here, Hart Island, was an old river meander. This below Skagit here, old river meander. This was an old river meander. Technically up here, this is Gage's Slough, also an old Skagit River meander. We have since sort of humanized it in the sense that we have continued to keep it clear, and it is meant as a flood fill protection system. Gage's Slough up here. It failed during the 2025 floods, and it flooded a lot of Burlington down here, unfortunately. That's a whole other topic. But Skagit River, just in satellite imagery, depicts how versatile and how dynamic it has been in the past. And it's not something to take lightly. So don't build a house on a cut bank. Oh, these are the Skagit River meanders right now. Some of them are older, some of them are newer, and then this dark blue line indicates where the flow is occurring right now, actively. My favorite story to tell, hold on. Okay, so this is one of my favorite pictures to show students, and I took this image. You know what? Hold on even more. Hold on even more. Okay, this is beautiful because I'm pretty sure I took this image on Google Maps. I don't want I 3 or 4 years ago. Because I've been teaching this lesson for so long. And I've just been using a lot of the same slides, and this was perfect. It ended up perfect for me. So if you drive up the North Cascades Highway, which again, highly recommend, one of the most beautiful highways I've ever been on. Here's Highway 20 and North Cascades Highway. Here's the city of Lyman. You're going to pass by the tiny town of Lyman. It's not a big town, but there's signs to it, so you'll know where it is. And I want you to look at Lyman 3 or 4 years ago. Here was Lyman 3 or 4 years ago along the Skagit River. Now, keep in mind, when they built Lyman, I don't know, 100 years ago, it's a big logging town, which is how Skagit sort of got started. It's one of Skagit's beginnings is logging. So the town of Lyman has been here for a very long time. They did not build it on the bank of the Skagit River. But you'll note, this area here on the Skagit is along a cut bank. So Lyman's kind of fucked. And in fact, during the floods, Lyman and Hamilton's just a little bit further, wait, this way. Sorry, I'm doing it on my video. So it's further up the North Cascades Highway. Lyman and Hamilton get really flooded every flood season. So this was how it looked 3 or 4 years ago. And the reason I put you on pause for a second was so I could show you. Here's what it looks like now. Actually, let me see if I can get both up on the same screen. Compare and contrast. So the cut bank is sort of shifting in this direction, which is away from Lyman, which is good. But look at this channel here. Look at how much bigger it is. And this was an image that was taken in 2026. So here's what it was in 2023, we'll say 2023. Here's what it is now. And well, it would have had to have, this image would have been taken after the floods because the floods happened in December 2025. So this river, this stream channel grew just from 2023 into 2025. So Lyman's not doing so hot. Don't build a house in Lyman. Sorry, Lyman people. It's not doing super great. Yeah, there you go. So just something to keep in mind. Cut banks are incredibly dynamic. These river systems are incredibly dynamic. And just looking at 3 or 4 years ago, they're going to change dramatically. It's so wild to me. But so cool all at the same time. So with these streams, we also get sediment transportation. So I want you to think about, oops. Sorry, I'm getting a phone call from my dentist. Okay. So we're going to talk sediment transport. So, okay, I think I was talking about how, if you can imagine, water on its own with nothing in it, and it's hitting a rock. Do you think that rock is going to erode based on something that is significantly less hard than it, right? Water is very soft. It's water, right? If that water is continually striking this rock, do you think it has the capacity to erode? It might erode from the acidity in this, or it might weather because of this acidity, so it might start to break down very, very slowly. But erosion happens very quickly, at least in the terms of stream systems. And what happens is the stream system, let me see what my next slide is. Okay, I guess this is a good one. The stream systems are moving so quickly that they're able to hold grain particles in its flowing water as it's moving. So the sand and sediment can actually stay suspended, that's what we call it, when it's suspended in the water, and these grains will hit different rocks and different sediment types as it moves down the slope. And those grains are what are actually eroding the banks at a much faster rate than just water would on its own. So this is Skagit River on a beautiful, clean, clear day in Mount Verney. Here is the Skagit River during the floods. It's very brown, it's very murky because it is carrying so much more sediment. When the floods occur, the water moves much faster. It's able to pick up sediment, any kind of loose sediment, and carry it with it uh, in its water column. And because of that, it is eroding material so much faster. So this was not me standing on the banks of the Skagit River during the 2025 floods, because that's incredibly dangerous. Don't ever do it. I would never. And filming the water as it comes past. This was very quick, or the water is moving very fast. We'll play it one more time because it's fun. It's moving very fast. It's carrying a lot of sediment. It's carrying a lot of debris. So I was not videoing it to get images and video of the debris that it was carrying along with it. Because of how fast it was moving and because of how high it was able to collect all this debris as it moved down the water, or down the stream system. But because it's moving so fast and because it's carrying so much sediment in it, it's eroding the channel that much faster. So these alluvial channels, they carry sediment with them. And then when the water eventually lowers, it deposits that material. So the energy has to be high enough to carry rocks, to carry pebbles, to carry sand. But as the water starts to lower, as meltwater depletes or when the rain goes away, all of those particles will deposit on the riverbanks. So in this situation, if the discharge and velocity of the stream to it were to increase very quickly, it would erode the sediments and change the shape and the position of the channel, as well as these bars, these braided bars between the stream system. So if we get a flood system and this water begins to raise, the velocity of the water is going to be faster and it's going to be able to move larger particles along the stream system, meaning that a meteorological event that could lead to a sudden increase in discharge is heavier rains. There are two types of alluvial channels. So we have our meandering stream in here. That's what it's asking is there's two types of alluvial channels. There's two types of stream systems. Alluvium is just unconsolidated sediment or material like pebbles, like rocks. It's unsorted. We talked about sorting last week. So it's unsorted. You'll note down here, there's piles of pebbles. We also have sand in there. We have silt. It's unsorted. That's an alluvial channel. It's when you have unconsolidated sediment that help build this channel. It's also just a stream channel, stream system. And we have a meandering stream here, but we also have this braided segment here. That's what this question is asking. So eventually, these streams make their way to the ocean. And this is what we're going to end on today because we've worked through our terrestrial hydrosphere. We're ending in our marine hydrosphere. And we're going to start marine hydrosphere in the next video. So we're going to end the terrestrial at the area where the river and the ocean meet. This is called a delta. Basically, here's the slope we have as the river is meandering down a valley system. It's moving. When it hits the ocean, the steepness gets like this. And because the steepness slows, the water then slows down entirely. And all of the sediment that it's been carrying from the mountains just deposits. And it deposits into this delta. So this is the Ganges Delta in India. This is part of the Himalayan deposit. So the Himalayas are in northern India, and the Himalayas are actually eroding very quickly because they're so high in elevation. So they erode very, very quickly. And there's a lot of sedimentation in the Bay of Bengal, which is down here by India, where the Himalayas are depositing and emptying out their sediment. The Bay of Bengal actually has the largest sediment fan, delta fan. It's underwater. We call it the Bengal fan. And this entire underwater fan of just sediment has come from the Ganges River, has come from the erosion of the Himalayas. My former advisor from my master's degree did a lot of work on the Bengal fan and studied how fast the Himalayas are eroding because there's so much sedimentation that is coming out into the water and just fanning out. This is all deposition from the river systems in the Ganges. Skagit has a similar one. This is Skagit Bay. I took this in 2024. Let's do this again. This is so fun. Hold on, hold on. And okay, it's not quite as dramatic as Lyman was, but so this was Skagit Bay in 2024. So this is when I took it in 2024, and this is Google Maps in 2026. So this is what Skagit used to look like. Let me sort of get it up to the same spot. And then this is what Skagit looks like now. And to be honest, Wiley Slough doesn't look that much different. But this area up here in 2026 looks a lot more established. And to be fair, I also don't know the months that these were taken in. So months might play a role, and tides might also play a role. But this looks a little bit more, not established, but defined. This little spitty here by Lucaner. But the way that deltas work is the land is going to grow westward as more sediment is deposited out into the bay. So you can see the sediment that is being deposited. This is all green, this is all marshland. But down here, this is where brand new sediment is being deposited on a regular basis from the Skagit River Delta. As that river system, we can zoom in even more. As this river system is entering the bay, this velocity of water slows down so dramatically that it just dumps all of the sediment from the river right out into here, into the bay. So you can see it. It's very visual. It's so amazing. It's incredible. Okay, let's finish the slideshow. Current side. Oh, I made that real dramatic. So here's the Wiley Slough in 2024. We looked at that. Oh, that was it. Cool. So that's the terrestrial hydrosphere. The next video is going to be about the marine hydrosphere and how we look at the ocean from a geological perspective.